All right. So, welcome to lecture 6. I hope you enjoyed your week off and have great progress on your coursework. Probably so far all done. We will talk about some general questions some of you may have tonight. It's a slightly longer version of our lectures tonight. We have about 90 slides. So most of them are just recap, so don't worry. And just a quick recap from last time. We talked about, is it too loud, the speaker? No? Is it good? Okay. Because I can hear myself. Previously I couldn't. So what we talked about so far is we talked about image classification, we talked about features. What sort of features we need from images so that we can use those features for understanding what's inside an image and how we can use edges, corners, color features and things like that. We talked about hug, blob, gobbo, bag of features models, and had an introduction to machine learning and learned basic supervised learning models such as support vector machines, neural networks, and you understood that in order to do a classification job, what you need is to extract features from images and send them to a machine learning model, like a support vector machine. So tonight we are going to talk about unsupervised learning. K-means is like many of the slides tonight are K-means, but I will just go through them because you all know K-means, we have touched it before. But we will connect the dots tonight. So far, whatever we have learned will be connected and we will see how things work together. We will talk about more advanced dictionary of more advanced feature extraction models. We will talk about SIFT and SERF, which are very, very practical, very useful. And, or better say they were very practical and very useful, but we will, next week we will see why they are no longer of that much interest. We will talk about dictionary of features, and then we can revisit the panoramic image creation. You remember we had an image from different angles from the same object and we wanted to stitch them together. So far we can't do that, but tonight we will learn how to do that. And we will talk about green screen because it's a long, boring lecture. We will talk about green screen to have some fun. So supervised learning, we said we have an environment. We have a teacher. Our system learns from the environment, extracts some features, learns a model, and produces a result, an output. If the teacher agrees with that, we are good to go. If the teacher doesn't agree with that, which means the label doesn't match the result that we produced, we generate an error. We say this is the error signal. We update what the system was doing, and then we do some iterations until all of the samples are correctly classified. So this is supervised learning when objects have labels. I have images of students. I know each folder is a student 1, a student 2, a student 3, and so on. They have labels. So that is supervised learning. I can train my model. If my model just classifies a student 5 as a student 7, I say there is a mistake. I retrain the model. So I have labeled data. But if I have no labeled data, but I still want to extract some information, I use unsupervised learning. So one of the methods for unsupervised learning that you're all familiar with is K-means, or generally clustering, which has several methods. One of the problems we have is clustering. One approach is K-means. So I want to cluster my data. I have some data which, like in a two-dimensional environment, they look like this, very, very simple. So ideally, I want 4 clusters of this data. But to use K-means, we realize that we will have some problems. How do I know I have 4 sources of data? Maybe I have 5. If I say 3 for this, what would these clusters look like? So deciding on the number of K is very important, and K-means doesn't do that automatically. So there are other things that we have to consider. We will talk about them. So K-means algorithm, generally as we talked about it, we said we have some points, let's say, here. And what I want to do is I want to classify them, to group them together. Say this is group 1, this is group 2, but I have no labels. I don't know the labels of the data. But, you know, visually, this seems to be one group and this seems to be another group. So what I do in K-means is I randomly choose 2 means. I say this is mean 1, this is mean 2. And by some magic that I have, I know these are 2 groups. So I have one here, one here. Then, for this particular one, I find all that are closer to this. I calculate the distance of this mean to all individual samples that I have, and I calculate the distances, and the same for this. I assign the closer ones to this, to cluster 1, and the closer ones to this, to cluster 2. And then I repeat. So what I do here is I update the mean. So if I have this red data, the mean of this red data is going to be somewhere here, and the mean of the blue one is going to be somewhere here. So again, for all data points, I calculate the distance to each of these means, and then I realize, okay, these guys are closer to this mean than to this mean. So I label them class 2 and label these as class 1. And I keep doing that until there are no more significant changes. So start with a set of endpoints, set k-means randomly. I randomly chose these 2 locations. You could choose k as one of your samples. It could be anything. You could say pick 2 samples, 5 samples, 10 samples. We will see how we can sort that number out as well. And then assign the endpoints to the closest mean, and then calculate new means for the, from the assigned points. And repeat this until convergence. We saw in, we can do this in image segmentation. We saw in lecture 4 that we could say in MATLAB k-means, and then use send your image as a column, and then k the number of clusters that you wanted. So if you set k2 for this panda, you will get 2, and if you set 3, you will get 3 different clusters, and these are the colors, like 3 different colored clusters here. So what are the pros of k-means? It is simple, it is fast to compute, and it is very useful. We will see, we are going to use k-means tonight later as well. But what are the issues? One of the problems is how do I find out k? So it is called the elbow method. We will talk about it. The other method, the other problem is how do I choose those initial centers, those initial cores? The algorithm that is used is k-means ++. We will see how it works very briefly. We are not going into too much details. And it is sensitive to outliers, and it detects spherical clusters only. So if you have an image like this, k-means is going to give you clusters like that, which is like visually you would say this is probably one cluster and this is another cluster, but k-means is going to give you that. So one solution for this we have already seen is change the dimensionality of the data or the coordinate system that you're using. We saw that if you go from Cartesian to polar, we could change that number and probably get better clustering for this. But depending on your data, you have to use different methods. So the other problem is outliers. If I have data like that, and if I say k equals to 2, then this is one cluster and this is another cluster, which the mean is going to be here, and I'm going to have a large internal variance from this mean to the other data. But if I say this is an outlier, just forget about it, and then I will magically have 2 clusters that are much more reasonable. So there are ways to deal with these. I'm not going into details much, but just to give you the general idea. So if for outliers, if you have some data and you see within the clusters that you are creating the variance inside those clusters, you can calculate the variance, like how far the distances to the mean is. If the variance in the cluster is too much and just one data point or a few data points are causing that variance, then you can eliminate those. For k-means ++, the idea is to spread the initialization. Don't choose those clusters like next to each other in your space, in this domain that you're working with. Try to spread them across the entire dimensionality of the data. So for each of these, if you like, you can just Google. There are MATLAB implementations in MATLAB Central. There is more detail. The other one for understanding the number of k is using elbow model. So in this one, what I do is I start from, let's say, 1 cluster, 2 cluster, 3 cluster, and do my k-means, and then calculate again the variance inside each clustering, number of clusters that I have. So in this one, if I have 1 cluster, the variance of the data is too much. If I have 2, it's here. If I have 3, it's less. If I have 4, 5, 6, and if I go from like 5 further on, I don't see much of a difference. So you see I'm creating an elbow. It looks like an elbow. So once you reach that elbow point, you can decide this is probably a good point for my data. Probably 3 in this case is a good number. So depending on how much k-means is going to be affecting your work, you can work on these more and more. You can do k-means plus plus, which MATLAB by default uses that for initialization, so that's the good news. You don't have to worry about that. But you can do the other models like the elbow to understand how many you want. One of the points that I mentioned here is that what we do is for all of the data points, I calculate the distance to each mean, right, to find which ones are closer. So this means in every iteration, if I have 1 million data, I have to calculate, and if I have 2 means, then I have to calculate 2 million calculations to understand where what the distances are. The good news is there are ways to make this faster. You can record the coordinates and make it faster, but still it is very slow. So this is called batch update, because you're updating the whole batch, right? You're taking all of the data and updating it. In MATLAB, what it does, it's in the first phase, it does the batch update, and then it does online update. So the online one is once you have some means, you have chosen some data there, then you go through the online one. You feed one data at a time. So what it would look like, something like this. So for every single one of your data, draw one. You have chosen random values for initial centers. Draw a sample from the training set. Find the closest one to that particular one and update the mean that is closer to that, and then find the next data entry. So in this way, instead of taking all of those distances and comparing it with the mean, I'm taking one instance of my data, comparing it to the closest mean that I find, the closest center that I find, and then I update that center, make it closer, reduce the distance, and then I take the second sample, find the closest mean to that sample, and update that sample. And I keep doing that. So in this one, I'm doing online learning, sort of. It's one by one. It is not a batch group, right? Is it clear? So what is the idea here? The idea is take one training sample, find the closest center to it, compare the distance, update it, move the mean closer to the instance that you have. Good. Now take the second training data you have, compare, find the closest mean, update that mean, and keep doing that. So in this way, I'm doing k-means as well. So this is in MATLAB, this is the second phase, and it is more prone to local minima. So if you have a local minima in the first one, you will get stuck in it. But with this one, because you're doing with individual data, there is less chance that you will end up with local minima. You have a better chance of finding the global minima, the best cluster centers. So keep this slide in mind. What we are doing is for every data entry, we find the closest mean. This is finding the closest mean, and I only update the closest mean. And then I take the next data, find the closest mean, update the closest mean. Next data, find the closest mean, update the closest mean. So what you can see here is I'm only updating the mean. That is the winner. So in this case, we call these models winner take all, or WTA models, because the winner is taking everything. That's it. I win, I update. No one else updates in the model, right? So later we will see how we can change that. There is another model for clustering, which is mean shift. So in this one, this is quite similar to k-means, but the difference is for your data, you keep one sample, for example, and instead of finding the closest mean of the random initialization, you draw an area, let's say a circle or rectangle around it, and in that rectangle, you find this mass at the center of the mass, and then you shift that. Let's see how it works. So I have this data, let's say distribution of identical billiard balls, and I want to find a good center point, find a good mean for this data. So what I do is I randomly pick a number, pick a center point, and then I draw a region of interest around that. Okay, so this is a distance around that particular mean, cluster, center that I have chosen. I calculate the center of the mass in that window, right? And then I create a mean shift vector and shift my window. Again, in this one, I calculate the mean of this window, which is here. I shift it, right? Again, calculate the mean and shift it, right? So using this, I could find the center of the data that I wanted. So what we can do in real life is we can virtually set a window around every single point in our data and calculate those the mean of that area and keep moving it. And the ones that end up very, very close to each other, we merge them. So the idea of mean shift is also very simple. We can find features, whatever features that we have in our model. You can say color, you can say texture, whatever feature you have. Initialize windows at individual pixel locations. Perform mean shift for each window until convergence. And merge windows that end up near the same peak. So this way, I have also another way of clustering. And if you do your clustering on this image, this is your color features. And if you do that, you will end up with clusters that look like this. So this is going to be your final result, which is nice. And if you are interested in more details, personally, usually I put like a few slides of each concept, and then there is a 1-hour video. So if you are interested, you can dig deeper. But for your exam and for this course, you don't have to, as far as you understand what I generally talked about. So this is mean shift. Another way of looking at this is looking at clustering is using SLIC, as we talked about it in lecture 4. In this one, instead of working with single pixel values, we work with superpixels. So what is a superpixel? A superpixel is a few pixels around each other which are similar. So instead of working, if I have an image like that, instead of working, let's say this is 1,000 by 1,000, instead of working with 1,000,000 pixels, if I have groups of 20 by 50, something like that, 10 by 10, 5 by 5, and they have the same characteristics, I will group them together and then consider them as one pixel. So this will reduce the computational cost significantly. So instead of working with 1,000,000 pixels, you end up working with 20,000 superpixels. And then you deal with it exactly the same way. And the thing is, for each of those pixels now, you're going to have LAB or RGB, whatever you like. This is another color space, right? You can do LAB, RGB, and then you have two spatial variables, X and Y, because you want to know where they were in that image. Those are the group together, and then later you can put them back if you want to. So you will have 5-dimensional space instead of a 3-dimensional space. So this will reduce computations, and in MATLAB we just call superpixels. So it is already there. Okay, so I quickly wrapped up on k-means. So now you have an idea, if you didn't, that k-means is very useful for unsupervised learning. But what we saw was k-means is a winner-take-all. The winner, the one that is the closest mean, is updated, the rest are not. So there is another way, which is called self-organizing maps. This is biologically inspired, and it's sort of neural networks. So in our brain, as you can see in the motor cortex and in the somatosensory cortex, we have neighboring areas that are relatively spatial in terms of closeness. So you have the motor senses here, for instance, for the like your toes, ankle, and knee, and here you have the same area, and they are adjacent, they are close to each other in our brain. So the idea comes in 1973 as well, that Malzberg defined self-organizing property of the visual cortex. He believes that our brains, once a neuron is firing, it fires the neurons that are closer to it more, and the ones that are further away less. This is very reasonable, right? So how can we model this? If we want to, we are going to have something called self-organizing maps. It's a very, very simple implementation. It's almost identical with k-means, but there is only one difference. So what I do is in k-means, I initialize these centers randomly, right? I said I have j centers, j means, or whatever I wanted to find. So in this case, let's say we have 20 centers, right? So what I do is I put them in a grid, in a 2D array or 1D array. They usually do 2D for illustration. It's nice. So you can do put your arrays in a 2D array. So it's going to be neuron 1, neuron 2, neuron 3, and neuron 20, right? So what I do for my data is like the online bit for k-means. So what I do is for every input vector that I have, and these weights are randomly initialized, right? It's again like k-means. You randomly initialize some centers. So for this one, I find the closest center. So let's say this one is the closest center. All right? So far, is it clear? So I have an input, which is n-dimensional. And for that input, the closest center is this one. So in k-means, what I did was I would update this and then go to the second input, right? But here, I update this and I update its neighbors. The closer to this one, the more they are updated. And as you can see, this is red, these are like pinkish, and these are not really that much updated. So depending on the distance function that I decide, or how the neighborhood function that I decide. So again, same idea, k-means, but not only update the winner, but also its neighbors. So that's self-organizing maps. Simple as that. So there are, as we had in k-means, I randomly initialize all weights. So these are all the weights I randomly initialize. Then I select an input vector. This is my input vector, which is n-dimensional. I compare x with weights wj for neuron j to determine winner. So I compare that input to all of these weights that I have. I find a winner. In this case, this is the winner. And then I update a winner so that it becomes more like x. So far, k-means. Now this is the difference, together with the winner's neighbors. So this updates and neighbors update as well. And then I adjust parameters. Learning rate, what does it mean? Neighborhood function, we will see what they mean. So I repeat this until I have a convergence, or I have reached, say, 10,000 iterations and I don't want to do it anymore. So what I have here is 3 steps: competition, cooperation, and adaptation, synaptic adaptation. So competition, simple, determine winner, find the closest center, like k-means. Cooperation, update the winner and its neighbors. And adaptation is time-varying learning rate and neighborhood function. What does it mean? It means in the beginning, we will see this in deep learning as well. In the beginning, I start with a bigger learning rate because my data is random. I just want to update more neighbors to, try to make sense more of my data. But once the model has learned a bit, trained a bit, now I don't want those big jumps anymore. I'm trying to reduce the learning rate so that I converge, right? So imagine that if we have a marker, which we don't. Does anyone have a marker? No? Whiteboard marker? No? Yeah. I may have one here, but no, I don't. Never mind. So if we have the data that are spread and you're trying to update one, in the beginning you make big updates because you may be very, very far from where you want to be. But once you get closer to where you want to be, you reduce those update learns so that you find you just don't keep jumping here and there in your data space. You just get closer and closer until you are exactly on the point. So let's break down these steps. Competition, again, you find the Euclidean distance, you find the closest neuron. This is what we've had so far several times. just finding the distance between two vectors. And how do we do that? In Euclidean distance, it's just a very simple equation. If you have one vector that is a1, a2, and so on, and the other one is b1, b2, and so on, you calculate this, and you have the distance. There are other ways to calculate distance, but this is a typical one. And so now that I have the winner, I found the winner, I know which one it is, I define a neighborhood function. So this is a very good typical neighborhood function. So this is the center of it, the Gaussian. I have the central point, this is the winner. And the further I get, the less I update. So the closer ones are updated more, and the further ones are updated less. So, and this is again for finding the distance between two values. So you can calculate this d once. You don't need to do it every time. Calculate this because it's the distance between your input and the lattice that you have created. So you calculate these distances. You know the L and M and the N and K, which is for the neuron at position L and M, and the one at N and K. So you update them. So, as I said, as time goes on, we reduce the updates. So I want something like this. So initially I want something like this. As time goes on, I want something like this. So what I need to define is another time varying width. So my width is going to be updated like that. So as time goes on, this is my time. As time goes on, it's going to get like more shrunk. So that's very, very simple. I'm going to change that equation for the Gaussian into like something like this. So the sigma is a function itself. So now I have a time varying neighborhood function. As simple as that. So as time goes on in iteration 1, if time is 1, I calculate sigma, I calculate the distance, and I update the neighbors. The second iteration, t is 2, then this way the sigma is updated, this updates, and then I calculate the distance. So now it is very simple. I have the update rule, which is like what it was before. So if I want to break this down, the new weight of the winner is the old weight of the winner plus the neighborhood function, which is time varying, of the update rule. And this is my learning rate. Again, as time goes on, I reduce it. So initially, I have a higher learning rate. And as time goes on, I make it less. So in this case, I'm making like, again, here, I have a T2, which is another time constant to control the decay rate. So if I want to summarize self-organizing maps in one slide, we are going to go through this together. For n-dimensional input space and m output neurons, randomly initialize the weight vector wi for neuron I from 1 to m. Then I have sampling. Choose an input vector x from the training set. Determine winner neuron. So far, k-means. Update all weight vectors of all neurons I in the neighborhood of the winning neuron Ix. So in this case, not only the winner is updated, all other neurons are updated. But the ones that are far away, they have a big distance, they are going to be updated much, much less. Sometimes this may be even 0. So you don't update those. They are just what they were. And as you can see, it is very similar to k-means, but it is not the winner take all. Okay, so I think I explained self-organizing maps in like 10-20 minutes. It's usually a few lectures if you want to like go through with a lot of detail. But was I clear? Did you understand it? Yep. Yep.
So the weight vectors start looking like the input vectors?
They would, yes.
What's happening?
So let's say you have 10,000 colors, right? 10,000 colors in your image. You have all the ranges from dark blue to light blue, all the range from dark red to light red, right? And so on. You have 10,000 colors. And what you want is 20 colors. So what is going to happen is you randomly initialize those 20 colors. You say they could be anything. And then you take the first one, and now let's say you see a bright red color. You update that random one. Let's say the random one was black. And now you're updating it with a bright red. So it gets like a darker red tone. Then you update it with the second one, third one, fourth one. And so what you have is in all the dark and bright red range, you are going to find a mean, which is red, for example. So you have red as one of your centers. Let's say the other area that you were looking at, another cluster, is blue, is gray. So what happens, if you do k-means, and you know you want 20 colors, you will end up with 20 means that represent the 10,000 colors that you had. But in this case, what happens is the colors that are closer to each other are going to end up closer to each other on the map. So in k-means, if I do 10,000 colors into 20 colors, I may have the first mean red, the second one black, the third one orange, the fourth one blue. But in this case, you will see red, then maybe orange, then maybe pink, then maybe yellow. You see? So the closer colors are grouped together. So if you have data that their spatial relationship is important for you, so for example, you want to classify, let's say you have 10,000 bottles of wine, and you have all the data from the age as well. And you want to cluster them according to their age. If you do k-means, you may have the first one as a 2000 made, 1988, 2015, they might be random. But if you do a self-organizing map, because you're updating the neighborhoods as well, you end up with something like 1988, 1989, 1990, something like that. So the data will be closer to each other. The ones that are in a spatial dimension, they are closer to each other, are going to end up as closer clusters to each other. So this is the main difference here, right?
Maybe I'm misunderstanding, but convergence? What's the difference between kings and so on convergence? Is it the same principles, or
yeah?
Because all the what are they called in this situation? What means?
Yeah, it's the same thing. It's the same thing as k-means. Everything that applies there applies here as well. If you have to have 2,000 clusters and you choose a lattice 50 dimension, you're going to end up with the same problems. But the thing here is, the only difference we see here is that the numbers that are closer to each other, the neurons, the means that are closer to each other, make more sense to each other. It's going to be colors that are closer. So again, for convergence, you keep doing this until all of, like, your learning rate is very small, or your neighborhood function is very small, even for the closest ones. You keep doing that until you say, I want 10,000 iterations, I want 100,000 iterations. So, yep. What do you mean by a hard decision boundary?
Like involving calcium mixture model.
Mm-hmm.
Harsh is just like a soft boundary, which based on probability. This situation is, I get this vector. It's only got the signs of the one. It can't make an inference of what's probably the standpoint most likely color it needs to be assigned to.
So what we have here is we have some randomly initialized means, and we just find the closest to that. So it's just that. There is no other thresholding or hard decision board or anything. So you just find the closest, and once you calculate the distances with all, you find the closest and you say this is the winner, and then you calculate and update the neighborhood of that winner. So that is going to be the center. For that, D is going to be 0. But for the rest, so in this equation that we have, in this one, for the winner, D is going to be 0. So this is always 1. But for the rest, D is larger. So this is going to be smaller than 1. Right? So they are less updated. So in MATLAB, you just say net is self-org map. And you decide on the sizes, how many clusters you want. In this case, I want 8 by 8 cluster, 64. So it generates an 8 by 8. There is an example in your lab notes tonight. You are going to import the data set from MATLAB and just play with it. And it just goes like 10,000 iterations. You can define how many you want. And it finds the clusters that you want. And you can see that they are spatially relevant. So if, for example, you are doing years, you are clustering the years of the product of your wine, we will see that the years that are closer are grouped together. And the further away, they are further away. And then you call train net and you give it your input data. All right. So that's it. You are a master in unsupervised learning now. So last week, we learned supervised learning, support vector machines, neural networks, and tonight, k-means and self-organizing maps. That's it. So what's next? So let's say I have some features. I have extracted from each of my images some hug features from last time. How can I use them? If I extracted 2,000 features from one image, and the other image has 6,000 features. You cannot compare them, right? Because for a support vector machine, your input data should have the same size. It's going to be in the same space, dimensionality. So what I can do is I can cluster them. I can find from those 2,000 input vector size, I find 500 clusters. And from the other one, 6,000 features that I found, again, I find 500 clusters, and now I can compare them. So you see, clustering is still useful these days if you are using traditional computer vision. So we have talked about different sources for feature extraction. We talked about histogram-oriented gradients, blobs, gobbo, and so on. How can I use my features? As I said, there are two ways. This bit is important. Pay very good attention. You have two simple, there are more ways, but we're talking about two more important or main ways if you want to compare two images. Let's say I have some images of a cat and some images of dog. So for my dog image, I extract the hug features, or I extract the hug features from my cat image. If my images have the same size, I'm going to end up with the same number of hug features, right? But if they don't have the same size, or if I am using another feature extraction model which doesn't depend on the image size, let's say I have 2,000 from one image and I have 3,000 from another image. One way, as I mentioned, is to cluster them into 500 and the other one into 500 and feed them directly to a classifier. Okay? So I have 500 features from this one, and I directly feed those feature vectors to the classifier, and the classifier finds a line and says, give me a new input, I give it, and then it says, okay, this is a cat or this is a dog. The other way is to use a bag of words or bag of features. Bag of words is for text, and bag of features is for images. The concept is the same as we discussed before. I say, instead of directly feeding those 500 features for training me as a classifier, you have 100 dog images. Take a few, 2,100, 200, whatever features each image has, and take 2,100, 500 images from the cat images as well. Find a number that you want, number of clusters, and then you create something called a dictionary of features. So you have taken 500 clusters from each image from a dog, 500 clusters from each image from a cat. You have 100 images. You have 50,000 there, 50,000 here. You put them together. You have 100,000. Again, you cluster them. You will end up with something like 2,000, 10,000. So I have 2,000 features here as my reference point. Okay? Now I have a new image. Instead of taking those features and directly sending it to the classifier, I take those features from my image and then see how many times each of these 2,000 features that I have as a dictionary are repeated in that image. And I create a histogram. I say, okay, feature 1 knows I see 5 of that. Feature, I don't know, I see 20 of that, whatever, in that image. Maybe you have 10 dogs in that image. So that image is going to generate a feature vector for you, which is a histogram. So what would it look like? Let's say I have some images here. I create some clusters. One way is to just directly send those features to the classifier, and another way is to create a dictionary of features. This is what we have seen before. So for example, from this image, I have these clusters. I have taken patches from this image randomly, clustered them, and I ended up with something like this. I have taken patches from this image randomly, and I ended up with something like this. And I have taken from this one, clustered them, and I have something like this. This is for visual purposes. In reality, we don't use the image values directly. We extract features and do clustering on features. But let's say, for visual purposes, I have something here, and something here. So I put these together. I call it a universal text and dictionary because here is texture, or generally dictionary of features. So I have a dictionary of features. Now I see this image. How many times do I see this? I run this through this image, and I say, okay, I see it 500 times. How many times do I see this one? I say it 600 times. How many times do I see this one? How many times do I see this one? The closer one, maybe I found this one close to this, so this is 50, this is 10, and so on. So you see this feature vector is a very good representation of this image using this dictionary of features. So what I have done is I have taken some clusters from each image. I have created a dictionary of features, find the frequency of each feature, create a histogram, and then this is something that I can send to a classifier. I can normalize this and send it to my classifier. And this is very clearly separable for my classifier. This is much easier for it than this. And imagine you have an image of 1,000 by 1,000, a million dimension, a million pixels, but now you have only, say, 10. So your histogram is 10 dimensions. So it's going to be much faster for classification. So your classifier doesn't need to find a line in the 10 million dimensional space. It just finds something in the 10 dimensional space. Yep.
So maybe we'll come back to this later, but I'll ask it now anyways. So you have a person's face and you surf, and it has, let's just say 12 features that comes up. So you get the descriptor, which is, let's say, a vector of like 20. And I'm confused about how you then do clustering on the descriptors, which are, again, all individually different. No, they're all, I guess, technically the same length, but they're all vectors themselves.
Yeah, we will get there. Yeah. Okay. So for bag of features, what I want is extracting some features, learning a visual dictionary or vocabulary, and then quantize my features using that dictionary, represent images by frequencies of visual words. So again, for a very rough example, if I have this dictionary of features, let's say I have images of face, images of bike or guitar or violin, whatever. I take some features from each image. These are again visual, just for visual purposes. You don't see features like that, because this feature is maybe more related to a bike part than an eye, if the person is facing the other way around, so things like that. Anyway, I create these frequency vectors and then send them to the classifier. So what I do is, let's say I took 500 clusters from my image 1, I took 500 clusters from my image 2 and 500 clusters from my image 3, but I want to reduce the size of my dictionary, so I cluster them and I end up with something like this. So each of those inputs are going to be representing or represented by one of these. Okay? So this is half of your answer, but we will get to the other half. So what I need is I need to learn a visual vocabulary. But the problem is how to choose vocabulary size. How big should my dictionary be? How many features should I encode? 1 million, 100? That's a big question. If it is too small, my visual words are not representative of all patches. And if it is too large, quantization artifacts, overfitting, things like that. What does overfitting mean? Overfitting means that my system is no longer learning, it's memorizing. So what I want, if I give it an image of a cat and an image of a dog, if I give it all those images and I give like a 1 million dimensional dictionary, then my system is just memorizing that. It doesn't need to learn anything. It just memorizes, it has room for that. It just memorizes, this is a cat feature, I have seen it, and then once it sees it, it says I have a cat, and this is a dog feature. But if you have something that is more compact and representative, not too small, then your system has to learn, not memorize. It will understand the features that are more representative of a cat, so that if it doesn't see the identical image that it has seen in training, it will still work. So that is overfitting. It means your model is way too much tuned to your training images. That is why we have that validation set. We don't let the system see all of our training images. We let it see most of it, learn from it, and then test it on unseen images. And if it doesn't work well, we keep doing updates until the model doesn't memorize, is learning. So this is the more important concept. If I want to store a spatial information as well, I can do it by so far all of those methods are not using any spatial information. So they take one feature from anywhere in your image and they don't care where in the image is. So one way is using a spatial pyramid representation, which is an extension of bag of features. So you will have different levels for your dictionary. So you can have dictionaries that are split in spatial locations. But encoding spatial locations sometimes is a bad idea. Because if in my image the sky is here, for example, and then I have another image which this bit is also a sky, then it's going to have problems. It won't understand. So it's a, very borderline concept, spatial information. Anyway, it is good to have it to some extent, but again, you don't want to memorize. If all of your training images have a bike here, and then you learn that in your system, and then you have a bike that is here, then your system will not be able to detect it. So that's the pro and con of it.
So with the, just finding it hard to, so with the features, are they going to be like a collection of pixels, or do we not exactly know what they are?
No, we don't do collection of pixels.
Yeah.
So the features can be edges, they can be corners, they can be hug features,
Okay.
or as in the second half of this lecture, we will learn SIFT or self.
Yeah. And so with words, it's quite simple. It's either the same word or it isn't. Would it have to, whatever it is that the feature is, would it have to match something exactly?
No, it will not. It will not match exactly. It will be very close to that, but it will not.
Yeah.
Unless it is one that you have already seen.
Yeah. And so is there like some sort of threshold?
Yeah.
You're looking at, like you said before, you got two types of images and you're doing classification between them. So you have to ensure that you have to have, you're looking at your histomaps, distinct multimodal distributions. Otherwise, in essence, this approach won't work.
I'm not following. So for this one specifically, or
So
for this one?
correct, yes. That's two separate images that you're trying to, or two different types of images you're trying to classify, and you have two histograms which are quite equivalent. Does that in essence mean you can't use this approach?
That means your dictionary of features is not distinctive. So if my images are from cats and dogs, and I have all my features in my dictionary from sky and trees, it won't be distinctive. It's not a good dictionary.
So would you use that then as a metric to see how much you should start increasing the number of features?
It's not. So it depends. You see, usually what we do is we create that dictionary of features from training data. You see? So you have 500 cat images, you take 5,000 features from those, you have 500 dog images, you take 5,000 features from those, and then you create that dictionary. So this is the idea that it should be a good start. But if you are comparing cat and dog and all your images are from cars and bicycles, those features are probably not going to be useful. All right, so I'm going to talk about one concept, which is a very important and interesting and easy concept, and then we will take a short break. So I'm going to talk about integral images, and it has been known to be important. So what does it mean? It means it is useful. Integral images. Let's say I want to multiply this feature on this face, this filter on this face. So this is 255 times 1 plus 186 times 1 plus and so on. And then 286 minus 255 minus and so on. So these values here, on the right side, I have to calculate all of them, multiply them by 1, which you can just ignore, just add them, and then multiply all these black ones by -1, or just deduct them. So if I have a 500 by 500 feature, I'm going to need like a lot of additions and deductions, subtractions. So what do I do? The concept here is I calculate something called an integral image. So what is an integral image? I create one image once so that the value in that image, this is no longer an image, this is just a matrix. The value in each pixel is the sum of all the values to the left and above. So if I have 1 here and 2 and 3, in my integral image I will have 1, 3, 6. It's very simple, right? 1, 2, 3. Once I add them, 1 plus 2, so this is 1, 1 plus 2, 3, 1 plus 2 plus 3, 6. So I calculate this image once. Did you get it? I wish I had a way to... Maybe I can do it this way. Okay, take a break. We will be back in 5, please. I create this for you. Yeah, sure.
With the back features, so for example, if you're classifying like dogs and cats outdoors, how do you, to ensure like you don't get like, if you're using like 50, how do you ensure like maybe like 20 or 25 of them are, the features aren't like trees and clouds? Is that done like through pre-processing, through cropping, or?
You can't. That's the problem. It may well be. That's why it's important to have those images focused on. So most of these data sets, the object is in the center of your image. And what they usually do, they crop that center bit and they use that for feature extraction. So yeah, and then once they extracted those features, then you can look for them all around your image. Yeah. All right, let's continue. So, integral images, it's a very interesting concept, and it has been seen to be important. So what we have is, once we want to apply something like these Viola-Jones filters on our images to find the, let's say, eyes, or you remember these filters, right? You said we had them in lecture 1 or 2. So what we have is, I want to multiply this box, the white bit on this image, and then deduct the black bit from this image, and see if that value is higher than a threshold. This might be, for example, a part of a nose, or so on. So these box filters are very important. So in order to do this, one way is to manually just multiply all these values or add them, and usually it's not 1 and minus 1, it might be 0.3 and like plus 0.3. So you might need a lot of addition, multiplications, and so on. So this is the naive way of doing it, and the more interesting way is to generate something called an integral image. So the good news is, in MATLAB it's just called J is integral image of I. So you don't need to worry about it, but it's very simple. It's not one of those complex ones. So what you have is, this value in your integral image is the sum of all previous values. So this is the example that I wanted to draw. So let's imagine this is my input image. Okay? So if I want, so these are the brightness values, 10, 20, 30, 40, 50, 10, 20, and so on, 20, 30, 40, 10, 10, 10, 10. So this is my input image, and I want to, it's more visible on that one than this one, but I'll make it, and not the design, I think that's a table thing, so I have to change the theme. Come on. Okay, so anyway, it is supposed to be 10 and 20 and so on. Not. So this is 10, 10, and so on. No, not visible in this one. So look at that one. So what I do is, it should be a very simple change. If, yep, okay. So just make it. Is it visible now? Okay. Just make everything red. Yeah. Okay. Yeah. Better. Sorry about that. So what we have is, let's say this is my input image, and I want to calculate the integral image. Good. So what I do is, this is 10 in my integral image, this is 10. In my input image, this is 20. In my integral image, this is 20 plus 10, 30. This is 30 plus 30, 60. This is 40 plus 60, 100. And then the second one, this is 10 plus 10, 20. This is 20 plus 20 plus 10 plus 10, 60, and so on. So I calculate this image once. Okay? It's very, very simple. You just do this calculation once. 120 is, how do we come up with this? This is, actually this is that number. Anyway, what we will have is, we will have 10, 30, 60, we will have 20, we will have 60, and then this is 30 plus 30, 60 plus 40, 100 plus 20, 120. Okay? And we keep doing that. So the logic is, you calculate the cumulative row sum, which is, you calculate this Sx and y is x, Sx minus 1 and y plus I x and y. And then integral image is this one plus this one plus this one. So it's just one quick calculation, just a fraction of a second. You calculate this number, this matrix. But how can I use my matrix now? I have that integral image, and let's say I have a box here. So I want to calculate the sum of the values in this box. How do I do that? I say this box is equal to A, which is this whole area, right? Minus B, which is this whole area here, minus C, which is this whole area here. And because I have deducted this area twice, it was once in B and once in C, I add it once. Did you get it? Right? Simple? So the sum in this box is A, this whole from A, from here to A, minus B, this area, minus C, this area, and plus D, this area. So now I have this box's value. So I want to apply this filter. What do? I have the A, B, C, D of the white region. I calculate the sum, multiply it by whatever number, 1, 0.3, whatever. I calculate this sum, multiply it by whatever number is needed in my filter, and then I say sum minus sum prime is this filter. So instead of doing millions of additions, deductions, multiplications, I now just do it once. Just A minus B minus C plus D. So you can imagine how much speed you're going to gain with this. It's a very, very genius idea. So what we have is only 3 additions here. For a 20 by 20, 24 by 24 detection region, the number of possible rectangle features is 160,000. And if you want to apply all of these Viola-Jones on all of the image, it would take forever. But you can use integral images and then do this whole thing in a fraction of a second. So this is called also boosting, because you're using an ensemble of weak classifiers and you're generating a better decision, like in what we have in cascading classifiers, for example. You could do that by applying these weak learners. These are weak features. So what you can do is you can use integral images. Have this in mind. We will get back to this. So another, if you remember from lecture 3, I think, we talked about edge detection, and one of the ways to do that was this log model. You remember that we could call f special log and then size of the image and the sigma that we wanted, and it would calculate an edge map for us. One way to estimate this log is called dog. It's a difference of Gaussian instead of Laplacian of Gaussian. So what I do here, you remember Gaussian filters again, right? We had those filters that we applied on images for blurring them. And we said if I use a small kernel, I'm blurring it a bit. If I use a bigger kernel, I'm blurring it more, right? So here, we take the same concept. We apply the bigger filter, we apply the smaller filter size, we have those images, and we deduct them from each other. It will give us an edge map, which is again a similar result to LOG. So what we get here is once I have a more blurred and I have a less blurred version and I deduct them from each other, those edges are highlighted. This is called edge enhancement. You enhance those edges. So have this in mind. Let's return to this problem. I have this image, and I want to find this book in this image. So visually, this is the book, right? But if you actually want to do it, what do we have to do? What do I need? I need more advanced features to do this. So far, the things that I know, they're not going to be handy. So how do I do that? What are the things that I need? I need something that if it doesn't see the whole picture, it still can find it. So it should deal with some sort of occlusion for me. I want it to be rotation invariant, no matter what the orientation of this book is. I want it to be a scale invariant, because in this image, my book is very big. If my image is, let's say 500 by 500, my image is 500 by 500. But in this one, my image is maybe like 100 by 200. So it's a much smaller version of this, right? So I want it to be a scale invariant as well. One way to do that is SIFT, which is a scale invariant feature transform. So how does it work? It is some sort of features in your image. It extracts them and then it aligns them so that you can be location invariant. We will get into more details for SIFT. So if I want to match this image with this image, what I want is features from both align them, and then match them. So this is what we are going to learn now. How do I find SIFT features? So they have to have locality, distinctiveness, quantity, efficiency, and extensibility. So they have to be fast. It should be possible to find many of them in one image, and they have to be distinct so that they can help me detect the cat and the dog from each other. And they have to be robust to occlusion and clutter in the images, so they cannot be so big that if I don't see the whole book, then I won't be able to detect that book anymore. So a scale invariant feature transform, it's invariant to scale, to rotation, to illumination, and a little bit to deformation, but not much. The interesting thing is the number of citations for this paper. It has over 50,000 citations. So you can imagine one of the things that I have to look up every year is to look at this number and update it. So like 4 years ago, it was like 40,000 and 45,000, 50,000, so on. So this keeps growing. And this is 1 hour and a half, 2 hours lecture, I think, for SIFT, if you want more details. But don't worry, I will go through that. So, and you will enjoy learning it, as this is important. So what we want is a feature descriptor that provides us some invariance to all of the bits that we discussed. So basically, SIFT has 6 steps. Enforce invariance to scale. How do we do that? I'm just going to outline it so that you don't be scared. Don't be scared of it. Enforce invariance to scale. You have one image. Instead of only working with that image, make that image smaller and smaller and smaller and smaller, and work with those smaller versions as well. So this way, you are getting invariance to scale, right? If you see me this size, I am, let's say, 2,000 by 3,000 pixels. Reduce the size. Now you're looking at, I don't know, 1,000 by 1,500. Then reduce it again, 500 by 400. So if my arm, let's say my arm is a feature. If in one image my arm is a long feature, in the next one it's going to be a smaller and a smaller and a smaller. So if you see my image in any size, you will be able to find my arm, if that is a feature, for example, right? So invariance to scale is achieved by generating different scales of the image. Then I want to find corners. So I find corners in that scale space. For each of those scales that I have, I find the corners. Make sure they are not on the edges, because we realized previously that edges are not that important for features. Corners are much more distinctive. So I see if anything is on an edge, I eliminate it. I find the corners. So far I have found the corners. Then enforce invariance to orientation. For the neighborhood around that corner point, I calculate something like the hog, right? See the orientation of each point in that area. You remember how we calculated the orientations, right? So I calculate the orientations, and I see the dominant orientation in that area. And then I align everything vertically. So if I have my arm in that orientation, I calculate it, I say, okay, this is the dominant orientation, so I keep it like that. Then if in another image my arm is like this, and I find it, I say, this is the dominant orientation, so I align it like that. So if I have my features in any orientation, once I detect them, I find the dominant orientation and then align them vertically. And then I get a neighborhood around that, create a feature like hog, say, okay, this is a 128-bit feature around this area, and that's a SIFT feature. So you see, idea is very simple. So now you can have a paper with 50,000 citations. And then you normalize that feature vector so that it's more invariant to illumination, stuff like that. So a bit more details into each step. Enforce invariant to scale. As I said, I have my image. I create, so this is my image, and this is the blurred version. This is more blurred, more blurred, more blurred. And as you remember from dog, difference of Gaussian, if I get this one and take another one which is more blurred, deduct them, I have an edge map, right? So this is, at the same time, I'm creating, so this is bigger image, smaller image, smaller image, And at the same time, more blurred, more blurred, more blurred, more blurred. And once I deduct this version from the more blurred, I'm going to have an edge in different blurriness. So this produces a kind of scale space pyramid for me. So it's very simple Gaussian equation. So I have these blurred versions and I have these edge maps. So once I calculate this edge map, so a bit more detail, the idea is to find corners but a scale invariance. So I run a linear filter, like difference of Gaussians, at different resolutions of image pyramid, right? So this is a bit more detail, which we can have a look. So now I want to find corners. What did we do previously to find corners? I have, first of all, I want to find the points that are very different with their neighborhood, right? This is the first step. To see whether they are, like, what would it mean if I have a point here, and this is very different? I would say this is an important point, right? So this is an edge, probably. So the first step is to find the points that are very different with their neighborhood, okay? Which means there is probably something. So what I do is I look at my image, and for every pixel, look at 8 neighbors in that scale and 9 above and below. And if that pixel value here is less or more than all other neighbors, I see this is probably an important one, right? Because this is probably a very sharp value here. If everything around it is very low, this is probably an important, this is maybe on a corner. Okay? So if this value is bigger or smaller than all the neighborhood, the minima or maxima, I say this might be an important point. I call it a dog extrema. So in an image like this, I end up with something like this. I have 830 possible points. The next step is to make sure that the point that I have found is not on an edge. So I need something like corner detector. You remember we had Harry's corner detection? So the idea is again very simple. We said this is a corner because if I have any movement, the values in that box will shift significantly, will change significantly. But in this one, if I move along the edge orientation, they won't change and so on. So the Hessian matrix here is the second order derivative of x, xx, xy, xy, yy. Then you calculate the trace and determinants of the matrix, and you calculate, you find the lambda values and you calculate r. I don't want to go into details, don't worry about details. Generally, the idea is if r is greater than a number, then you say this is probably not on a corner. So what it does is it's saying if you see some pattern like this, you're probably looking at an important point. If this is producing a good result, this means you're on a corner, right? So after doing that, after eliminating edges, I find corners. Don't worry about details, it won't be that important. So what you have is, but you need to know how it works, but you don't need to go to exact details. So what we have here, we have detected the corner. So now I have 500 points. So there are a few other steps that they are a bit more complex. I have eliminated them, but they are basically trying to find out, is this point really significant? Is this a good key point? So you do that, you see if it is over threshold, the values and so on. So what you have so far is the points that you think are important. Okay? The thing is, they are on a corner. They are in a scale space, they are in a corner. So you found corners in a scale space. Nothing that significant so far. The next step is finding the canonical orientation. So for that area that you have selected, so for the, we create a histogram of local gradient directions computed at selected scale. So on that scale that we found that, we calculate the orientations around it. And then we smooth it in 36 bins around all of those orientations that we calculate. These are the equations. So to the right and left and above and below, we calculate the M and then we calculate the orientation, magnitude and the orientation. So this is similar to HOG. So what we do is we calculate the orientations, and for each area we find the dominant orientation. So if I have an image like this, for example, if my features in that area look like this is going to be the dominant orientation in that area. So what I do is I align it vertically. And if I have two dominant orientations, for example, one of them is like strongly to this orientation and the other one is slightly less but to this orientation, I keep it as two different features, right? And I store as two different features so that I have the second winner as well, like if they are 80% of the max peak. So I can have one or two or more from each area, usually one. So if this is the dominant orientation, then I rotate it and they say this is one, and then I have another one which is this is the bigger one, and then I have a second one. So I have that area, that bit around the corner, and I stored it vertically. And the rest is just like very simple methods. What you do is you compute a gradient histogram of the local image in a 4x4 pixel region. Orient so that largest gradient points up. Possibly multiple solutions. Feature vector with 4x4 by 8 gradients, if it converted into 8 different gradients, you will end up with a 128 dimension vector. And then you normalize it. So what you will end up is something like this. It's going to be a feature vector, which is, so the idea is similar to what we had in HOP. You calculate the orientation of the neighborhood of a corner in a scale invariant environment, aligned. That's it, right? Not that complex, but I understand that you have to go through it a bit more, you look at more details. So in MATLAB, there is no direct implementation of SIFT, but there is a toolbox in VLFeed you can download, and it's a MATLAB toolbox, you can use that. The reason is SIFT is copyrighted, so there is a better way to do it. We will get to that. So once you have this key point descriptor, you have a 128 dimension vector from your image. So you have one image, you may end up with 500 SIFT features, you may end up with 200 SIFT features, you may end up with 10, or you may end up with 1,000. It depends on your image. If you have more corners in that image, more features that are distinctive, and depending on the resolution, you will extract different number of SIFT features. So one way to use them is you can now match them. So if I found a SIFT feature here, and I have SIFT features here from this Fontana di Trevi image, I can find those and see which one is closer to this feature. And then you can match them. So you can, now you see it makes more sense. Things are getting connected. So what we have is a scale invariance, is rotation invariance, HOP. We can briefly call it that, right? It's orientation of the vectors around the pixel that was a corner aligned vertically. And once you have everything aligned vertically, now you can compare them. And it doesn't matter anymore if it is oriented, if it is big or small, you can still find that or compare them. So for distance of these, you can use any distance matrix, but usually they do the sum of the square differences, which is what you have seen several times so far. There is another implementation, which is very similar to SIFT, which is called SERF, speeded up robust features. This one is quite similar to SIFT. The only two differences is the way it estimates the Hessian matrix and uses integral images. So, and also on the, so this is the same thing, and the other one is the way they calculate the different filters. So we will talk about that. So SERF is also an important paper. It has about 14,000 citations. And the way it works is it uses some genius ideas and makes SIFT much, much faster. One genius idea is integral images. Let's see how they can use that. So you remember we had a matrix like that for the Hessian. So we were generating something, a filter, a box filter like this, right? But what it is a 9 by 9. But if you want to estimate that or approximate that, you will have something like this. Similar to this, you will have something like this for LXY and for LYY, for example. You will end up with something like this. This is a simplification of that. So if you multiply this instead of this, you can imagine how fast you can be. So this is LYY in that matrix, and this is LXY in that matrix. So instead of multiplying these filters, you will have just a box filter, and instead of multiplying all those numbers all over the image or around that key point, you will only do this box filter, and you know how fast this is. So this is one approximation. The other thing they do is in SIFT, images are repeatedly smoothed with a Gaussian and then subsequently subsampled. But in SIRF, instead of using different scales of the image, they use different scales of the filter. Because they are using integral images, and then they use a different filter size, and it is still the same amount of calculation. So it would be faster. In MATLAB, you can say I is IM read, points is detect, serve, features I, that's it, no more worries. And then show the image. So it finds the, you can plot the select strongest points. You can choose the top 10 strongest, the ones that have more strengths, which means the values of the orientations and magnitude in them is higher. So if you want more details, this is a paper you can look at, but don't worry too much about the details. So what you need to know is what they basically are. SIFT and SIRF are basically models to extract features from images which are invariant to scale, to rotation, and in SIRF we use integral images. This is the gist of it, right? So that once you are applying it, because tonight I have a slide which does half of your coursework, so once you're going to apply that, you will know what it means. Oh, I see some laughter, good. Okay, so how can I use SIFT and SIRF in bag of features models? They are very good key point descriptors for bag of features. You can use them, you can extract features, and you can bag them, create a dictionary of feature, and then compare them. So we will see how it works. So in MATLAB, there is a function called bag of features. So what does it do? It extracts SIRF features from all images in all image categories and constructs the visual vocabulary by reducing the number of features through quantization of feature space using k-means clustering. Life is simple, right? So what you do is you give a data set to it. It finds SIRF features from all the images in all categories. It selects some from each category. It puts them together, clusters them, and gives you those features. Simple. And this link here is going to be an example that you can use for your coursework as well. So what we have is I have some images. I extract SIRF features from them, create a dictionary, and then I compare my features that are extracted from a test image, which now I don't know what this is. I compare it with that dictionary, and I have a feature vector, which is sent to the classifier. So let's look at your coursework. So here is an example. Let's go through this together. So what this bit is doing is it clear, right? Yeah. Okay, so what this bit is doing, it's just getting a URL for Caltech 101. Okay? This is a data set that we are all familiar with so far. It has 101 object categories plus one background category. This bit, all here, up to here, is just preparing training and test sets. So it says if I don't already have this folder, download it, save it here. Now this is my root folder, and now these are the categories that I'm interested in. So this example is looking at airplanes, ferry, laptop, for example. Then you create an image data store, which is MATLAB's way of handling large data sets. But this is not that large, but this is a good way to use image data store. Then it counts each label and finds the minimum number of images in each category. Why does it do that? Because if I have 10,000 airplane images and I have 10 bikes and I get 20 features from each airplane and I get 20 images from each bike, my dictionary of features is going to be biased. It's going to classify more things as airplanes because it's not fair. You don't want that. So what this is doing is finding the minimum in each class, the minimum of all classes, to make sure that it is not unfair. And also, the other thing is, if you are training your model, you have to make sure that the model is trained equally. If you train your model with 500 cat images and with 2 dog images, your model learns to ignore those 2 images. Because if it classifies them correctly, it's only making 2% better results. But if it doesn't, it's already getting 98% results. So it doesn't care for that. So your model is again biased. So you make sure that you are using the same amount of training images per category. So here what we have is splitting each label, and you split them into training set and validation set. So this is my training data. I'm taking some from each class. I'm creating a training set and validation set. And the rest is not that important up to here. This is the key line. Bag of features training set. That's it. 50% of your coursework. So bag of features training set. So it's their training set, which is face images, in this case Caltech 101, and it creates a bag of features from your images. And we said, what does it do? It extracts SIFT features from all images in all categories and then clusters them. So once you have this bag, you use category classifier is train image category classifier, training set, and the bag. So this function, train image category classifier, uses a support vector machine, and what it does is for each of your training images, extract SIFT features, compares it with the dictionary of features, creates a histogram, trains the classifier. So once you run these 2 bits, you might have to wait a bit, because these 2 lines are, if you want to write it yourself, it's going to be much longer. And it is very much encouraged to do so if you have time. Because using these 2, you have to know what exactly is happening as one part of your coursework. But if you can implement these steps as well, that would be nice, but you don't have to. I don't want to put too much pressure on you. So you can use bag of features and then category classifier. And MATLAB makes life so easy. It has conf matrix is evaluate, category classifier, and training set. So it generates a confusion matrix. It tells you how well your model is doing on the training set and on the validation set. And once you have a new image, let's say I'm going to test image 0690, I read that image, and then I call predict. I call my classifier and the image, and it generates the labels for me. It says what your result is. This is the label, and then I say, okay, now convert it into text. What does it mean?
Isn't all this stuff part of Lab 5?
Yes. But in a different implementation. There's a lot of similarities. For example, in this one, I have provided two different ways of reading your data set. One was the manual one, where you read the directory, you find the folders yourself, you create the training and test sets yourself, or this one which does it automatically for you. So there are some differences here and there. But yes, that's very, very good point. So what you get is it predicts that label for you. What you need to do for your coursework, what I will need, is I need to have this category classifier, right? I don't need these bits. I don't need to, you have to include that in your code, but I don't need to run them. You have trained your model, right? And you have generated this classifier. So you right-click on it and you save it. And then you only give me this classifier. You can save it as a compact version as well. And what I do once I'm examining your code, what I do is I download this, I add it to my MATLAB environment, and then I call whatever function you're supposed to write, upload your classifier, and give it my test image. So you see, you don't need to give me your training data, because it's going to be a lot of data, and I do not need to train your models. Your models are trained. You save your classifier. You give me those lines. You tell me this is the lines that I found. That is your classifier. And once I want to use that, I only need to run this bit. Okay? So, for panoramic images, you remember we had this example. We previously couldn't solve it, but now with SIFT and SURF, we can find the points that are matching. And in MATLAB, it's also very simple. It's called match features. So you find those features from image 1, you find the features from image 2, and then you call match features, it finds it. And there is, in your lab, you have an example of how to stitch these images together. So now you're going to estimate the geometric transformation that you learned in lecture 2. So once you have this point and this point, this point, this point, now you want to see how that image needs to be rotated or, skewed and things like that, so that you can overlap it on the previous image. Okay? And so this is a bit of a bonus, because you got a bit tired tonight. So I'm going to show you the green screen. So we talked about this before. It's sort of a segmentation, the chroma keying. You have a background, green, and what you can do with it is you find those green pixels, and you use that for replacing the new video or image that you want to superimpose on it. In your lab tonight, you will have some examples to play with this. You have seen in some chroma keying videos that they have some markers, they have some points. Those points are going to help the program to find the dimensions, to find the location, so they are predefined and they can use them. So these are some failures of this model. So this
High
is a bit of
temperatures
a fun.
today, up around 50. Plenty of green on this map. Why can't I wear green, by the way? Roby, he's here to help me out here. Woo! I can do the weather like this. This is the best. Can't use the green screen. I can do a headless forecast and just go like.
Wait, my sneakers don't show up either, do they?
Yeah, they don't show up either.
Okay, so this is how it works, and okay. So next lecture is going to be about biologically inspired image classification, the models that are kind of inspired from human brain. Just very briefly, I will talk about my PhD and postdocs, the ideas that might be interesting for some of you who are going to do PhD in this area, and see what sort of projects are out there. And this won't be in your exam, so don't worry. Then we will talk about HMax very briefly. This is hierarchical max. And then we will briefly talk about DBNs, deep belief networks, and mainly talk about convolutional neural networks. So this convolutional neural networks is now a state of the art in computer vision. Most of the recent classifiers are convolutional neural networks. So until 2013, those traditional, they're nowadays called traditional computer vision. Support vector machines, neural networks, SIFT features, SIRF features, they were a state of the art. So what you wanted to do from a data set was extract SIFT or SIRF features, run them through support vector machine, and voila, you have your results. And this is the best a computer program can get. But since convolutional neural networks started, which is a very simple idea, what they do is they have some kernels, but unlike our edge detection kernels or other kernels that we had through the images, they are randomly initialized. And they are learned from the environment. So the key point is you have 1 million images, 10 million images, you feed them to your network with randomly initialized kernels, and the network learns the values of those kernels, and you will have the kernels which apply to your images as feature detectors. So if you look at those kernels in the initial layers, they look like edge detection. If you go further, they are like corner detection, more advanced features like rotation, scales, and then on top layers, those features, for example, if trained on a face data set, they look like face parts. So that is really, really amazing how convolutional neural networks work. So we will work most of the next lecture on convolutional neural networks. Just a quick, there are a few slides for your coursework, but I see that you have no questions, so I'm happy everyone is almost done. But the general idea, again, just to give you now you have everything you need for your coursework, except for the deep learning implementation, which you will learn next week. So everything you need is your input frame. You have used a face detector. You find the faces. That's the face detection bit. You do the registration. Feature extraction. Now you can extract your SIRF features, for example. You can create a dictionary of features. Train your classifier. And then once you have new images, you extract the same features and then you send them to the classifier. So this is how this works, the general idea. So these are some frequently asked questions. Can data have different dimensions when fed to the classifier? No. Should I resize the faces, bounding boxes to the same size? No. Because if you do that, you might be stretching your faces. One face might be smaller, like rectangular area, the other one is a square one. If you change everything to the same size, you might be distorting them, and this may reduce your accuracy. But if you want to feed the images directly to the classifier as pixel values, that's not a very brilliant idea. What you want is extract features and then use those features for classification. Or the other way is to find the eyes, if you want to go even more deeper in each face, and find the ratio and calculate the face dimensions and crop that area around that for your face. This is if you have time. So to train a classifier, it is necessary to have a consistent number of corresponding features. So we talked about that. And if you can remove variation in your data, it will make it easier to classify. Trying to classify based purely on color may be a bad choice, since color is dependent on illusion. There are ways called data augmentation. So once you have your images, let's say I have 10, 20 images from each person, which is not enough. I don't get really good results. So what you can do is you can augment your data, which means you can manually distort your data. You can resize them, scale them, make them smaller, bigger, shift them, blur them, add noise to them. So these are the things that we do to images so that the model is not memorizing, or called overfit. You don't want a model that is overfit. So We will talk about these details next week once we talk about deep learning, because this is more important in deep learning. In deep learning, you need a lot of training images. So that is a way to increase the number of training images so that you can use them. And as I mentioned several times, we will not require the data used to train your classifier. I will not be able to train your model. So if I want to train each of the models you submit, and each of them take 5 hours to train, it won't be possible to mark, like your 95 students in this class. So it will take 3 months to run. So what you will need to do is you have your models trained and submit the trained model. I just load it, test it. You see the point? It's very, very simple. I will not need your data. I already have your beautiful faces. So the only thing I need is your train model. These details are explained just to make sure. And so explain in your report how you have generated your data set, how you have, what challenges you had, how you dealt with them, and come up with a good report. Definitely upload your report to the Moodle, but if your classifiers are big, it's more than 200 megs, you cannot upload it to Moodle. You can upload it somewhere on one of those file sharing services and send me the link and include the report. The reason I'm saying definitely include the report on Moodle is because if you don't, I won't be able to confirm that you have submitted your coursework, and definitely make sure that you have enough time for uploading, because it depends on which models you use. Some people went really did the extra 100 miles, and the models that they had were like 2-3 gigabytes, and they wanted to send it. And then I received emails like 20 minutes before submission deadline. Hello, I'm uploading. It says 3 hours remaining. And what should I do? So give yourself enough time. Have an estimate of your upload speed. Make sure you do not miss the deadline. So, yeah, that's it. Don't upload your training data. Definitely submit your report to Moodle. And if you are sending us a link, include everything in the link, so that I don't have to download your report or some part of it from Moodle or the rest in your folder. Everything in that link. One more important point, if you're using MATLAB, everything is in MATLAB. If you're using TensorFlow for Python, everything is in TensorFlow in Python. If you're using PyTorch, everything is in PyTorch. Do not go cross-platform. It won't be simple and easy to market. So, yep, that's it. If there is no questions, I will see you in the lab. Thank you.